This is a cordless drill. In this video, we'll take a close look at the mechanism inside to see how it works. Before we jump into the inner workings of a cordless drill, let's first look at the key components involved. Let's get started. Cordless drills are one of the most common and versatile power tools available. They convert electrical energy into torque and are mainly used for drilling holes and driving screws. This is the chuck. It's a self-centering 3-jaw clamp that holds the drill bits securely in place while it's spinning. Most cordless drills use a keyless chuck that is hand-tightened by simply gripping and rotating the outer sleeve. A clockwise turn tightens the chuck, and a counterclockwise turn releases the bit. The chuck size on cordless drills is generally 10 or 13 millimeters. This is the clutch collar that lets you adjust the drill output torque settings by simply turning the collar. The main purpose of the clutch is to keep you from overdriving screws and avoid cam out. The clutch collar has printed numbers all around. The higher the number in line with the arrow, the higher the torque setting. There is also a drill mode represented by a drill icon, which is the highest torque setting. When the drill torque reaches a predetermined setting, the clutch will slip and the bit will stop spinning. Lower torque settings are suitable for driving screws into softer materials, while higher settings are for harder materials. This is the gear switch. Typically, drills are equipped with a gear switch, allowing you to switch between low and high speed settings. In the low speed setting, the drill operates at a higher torque, which is used for tasks like driving screws. In the higher speed setting, the drill operates at a lower torque, which is suitable for drilling holes. This is the trigger switch to operate the drill. Most drills have a variable speed trigger, meaning the more the trigger is pressed in, the higher the speed of the drill's chuck. Just above the trigger switch is the forward-reverse switch that slides in and out to change the direction of rotation of the drill bit. This is the rechargeable and removable battery that powers the drill. Today's cordless drills use lithium-ion batteries. They are spec'd according to two main characteristics: voltage and charge capacity. Battery voltages for cordless drills commonly range between 12 and 20 volts. Generally, higher voltage indicates a more powerful tool. The charge capacity is measured in amp hours, and it refers to the amount of energy the battery can store and provide over time. A higher amp hours rating generally means longer runtime, but batteries tend to be physically larger. The charge capacity of cordless drill batteries usually falls within the range of 2 to 10 amp hours. The inside of each battery contains a group of individual cells wired together, which look like AA batteries but larger in size. One of the most common lithium-ion cell types is the 18650 cell. The name derives from the cell's dimensions, with a diameter of 18 millimeters and a length of 65 millimeters. The nominal voltage of each 18650 cell is 3.7 volts, with a maximum charging voltage of 4.2 volts when fully charged. Adding more cells in series will increase the battery voltage by roughly 4 volts, and connecting them in parallel will increase the battery charge capacity. In this example, we have a 12-volt battery that contains 3 18650 cells wired in series. Inside the battery housing, a printed circuit board manages critical functions like charging and discharging, ensuring the safe operation of the battery pack. Now let's take a look inside the cordless drill. This is the trigger switch assembly. Inside, there is a printed circuit board that increases the motor voltage the deeper the trigger is pressed in. The higher the input voltage of a motor, the faster the output speed. When you release the trigger, a spring pushes back the trigger to its default position, and the chuck stops rotating. When sliding the forward-reverse switch in and out, it operates a small lever connected to a rotary switch. This switch changes the polarity of the motor circuit, thereby altering the rotation direction of the motor. Setting the switch in the forward position will drive the chuck clockwise, while setting the switch in the reverse position will drive the chuck counterclockwise. There's also a center position to lock the trigger switch. This is the electrical motor that converts the electrical energy from the battery into mechanical energy. The electric motor is directly connected to a gearbox that transfers the motor power to the chuck, while increasing its torque and reducing speed. The gearbox comprises 3 sets of planetary gear stages connected in series. Each planetary stage consists of 4 main components: the sun gear, 3 or more planet gears, the planet carrier, and the ring gear. The sun gear of the first planetary gear stage is connected to the motor shaft. When it turns, it moves the planet gears that roll along the inside of the fixed ring gear. The planet gears are mounted on the carrier. Their rotation causes the carrier to spin at a lower speed than the sun gear. The back face of the planet carrier has a gear that acts as the sun gear for the next planetary gear stage. The output of one stage becomes the input for the next. Let's now understand how the gear switching mechanism works. The gear switch is connected to a shift arm that moves the ring gear of the second planetary gear stage to the position corresponding to the desired speed setting. When the second stage ring gear is positioned at the high speed setting, the planet gears and the external gear teeth on the carrier both engage simultaneously with the internal gear teeth of the ring gear. This locks the carrier and planet gears together, connecting the input and output elements together, bypassing the second planetary gear stage, lowering the overall gearbox ratio, resulting in a higher output speed and lower output torque. When the second stage ring gear is positioned at the low speed setting, the external teeth of the ring gear engage with internal teeth of the first stage fixed ring gear. This locks the second stage ring gear in place, enabling the second planetary gear stage, increasing the overall gearbox ratio, resulting in a lower output speed and higher output torque. Now let's see how the clutch mechanism works. Inside the clutch collar, there's a spring-loaded plate, pushing against steel balls that engage with notches on the back face of the third stage ring gear. When you turn the clutch collar to adjust the torque setting, you are essentially compressing or releasing the spring. This increases or decreases the pressure applied by the plate on the steel balls. When the drive torque exceeds the preset limit, the spring force is overcome, and the balls roll out of their notches, allowing the planet gears of the third stage to turn the outer ring. This action keeps the planet carrier stationary, stopping the bit from turning. The ratcheting sound you hear when the clutch engages is produced by the ball rolling against the notches on the ring gear. Finally, let's take a look inside the chuck. Inside the chuck, there's a threaded nut attached to the outer sleeve that mates with threads on the jaws. The outer sleeve rotation translates into an axial movement of each jaw, moving the jaw forward and inward on a slight angle, clamping down on the drill bit. I hope you found this video informative and interesting. If you did, don't forget to give it a thumbs up and subscribe.